We are stardust. Heavier elements like carbon and oxygen are forged in stellar cores, supernova explosions. Scatter these elements, forming the building blocks of new stars and planets. It all begins with gravity acting on vast clouds of hydrogen and helium. A molecular cloud disturbed by a supernova or galactic collision starts to collapse under its own gravity. Density fluctuations create clumps that attract more material, initiating star formation within these dense regions. As the cloud collapses, pressure and temperature increase. A protostar forms at the center, surrounded by a spinning disk of gas and dust, called a protoplanetary disk. Accretion continues until the core becomes hot enough for fusion. When the core temperature reaches about 10 million Kelvin, hydrogen nuclei fuse to form helium, releasing tremendous energy. This process, nuclear fusion, marks the birth of a star and halts gravitational collapse. The star enters the main sequence, a period of stability where energy generated by nuclear fusion balances gravity. The star's position on the main sequence depends on its mass, determining its temperature and luminosity. Over billions of years, the star depletes hydrogen and its core fusion slows down, causing the core to contract and heat up. The outer layers expand, transforming the star into a red giant. The red giant is much larger and cooler than the main sequence star. Hydrogen fusion continues in a shell around the inert helium core. Eventually, the core becomes hot enough to ignite helium fusion. Helium fusion, converting helium into carbon and oxygen, releases energy and stabilizes the star briefly. However, helium is consumed much faster than hydrogen, leading to another phase of instability. After helium exhaustion, low-mass stars eject their outer layers, forming a beautiful planetary nebula. The expelled gas is ionized by the hot exposed core, creating vibrant colors. The remaining core, a dense ball of carbon and oxygen, becomes a white dwarf supported by electron degeneracy pressure. It slowly cools down, radiating away its residual heat. Massive stars, much larger than our Sun, evolve much faster. They undergo a series of fusion stages, creating heavier elements like neon, silicon, and iron in their cores. Iron fusion requires energy. Instead of releasing it, the iron core collapses catastrophically under its own gravity, triggering a supernova explosion. The core collapse releases tremendous energy, blasting the outer layers of the star into space. The supernova shines brighter than entire galaxies for a short period. In some supernovae, the core collapses into a neutron star, an incredibly dense object composed almost entirely of neutrons. These stars rotate rapidly and have strong magnetic fields. If the collapsing core is massive enough, it overcomes neutron degeneracy pressure and forms a black hole, a region of space-time with gravity so strong that nothing, not even light, can escape. Stars come in a wide range of masses, from tiny red dwarfs to colossal blue giants. Mass dictates a star's lifetime temperature, luminosity, and ultimate fate. The Hertzsprung-Russell diagram plots a star's luminosity against its temperature, revealing patterns and evolutionary stages. Most stars reside on the main sequence. Stars are classified into populations based on their age and metallicity, the abundance of elements heavier than hydrogen, and helium population. I stars are younger and metal-rich, while population II stars are older and metal-poor. Many stars exist in binary or multiple star systems orbiting a common center of mass. These systems can influence stellar evolution and lead to interesting phenomena like eclipses and mass transfer. Stars often form in clusters bound together by gravity. Open clusters are loosely packed and relatively young, while globular clusters are densely packed and very old. Some stars exhibit variations in their brightness, known as variable stars. These variations can be intrinsic, caused by physical changes within the star, or extrinsic, caused by external factors like eclipses. Cepheid variable stars have a period luminosity relationship, meaning their pulsation period is directly related to their intrinsic brightness. This makes them valuable tools for measuring cosmic distance. Stars possess magnetic fields generated by the movement of electrically charged plasma within their interiors. These fields can cause phenomena like star spots, flares, and coronal mass ejection. Stars emit a constant stream of particles called stellar wind, which can affect the surrounding interstellar medium and influence the formation of new stars. Many young stars are surrounded by circumstellar disks of gas and dust, remnants of the star formation process. These disks are the birthplaces of planets. The habitable zone around a star is the region where liquid water could exist on the surface of a planet, potentially making it suitable for life. Exoplanets, Planets orbiting stars other than our Sun are detected using various methods, including the transit method, radio velocity method, and direct imaging. In about 5 billion years, our Sun will exhaust its hydrogen fuel, expand into a red giant, and eventually become a white dwarf. Earth's fate is uncertain, but likely uninhabitable. Our Sun is just one of billions of stars in the Milky Way galaxy, a spiral galaxy with a central bulge, spiral arms, and a supermassive black hole at its center. Stars are the fundamental building blocks of the universe. They birth life and death-shaped galaxies and provide the elements necessary for life to exist. Studying stars helps us understand the cosmos.